A couple things I want to mention to you. We'll be doing iClicker in just a moment. I want to remind you that next Tuesday we have exam 4. And just to remind you, if you missed exam X or exam 3, you have got to be absolutely, positively at exam 4. Otherwise, you're going to be in the loser's corner, so to speak. In other words, this maneuver that we do at the end of the semester, we keep the best 2 midterm scores and drop the lowest. If all you got is 2, that's all you get. So if you've missed exam 3 and you're not here for exam 4, you're TOAST, toast. All right? But by inverse logic, almost like surface temperature logic, if you just invert the equation and think, if you're here for all 3, if you've been to exam 3, you've been to exam X, and you hit exam 4, and you crush one of them, then that means we dropped one of your stinky grades. And right now, most of you have got 2 exams on the books, and that's what you got. But after Tuesday next week, you'll have 3 exams on the books, and one of them, most of you, is out of here. All right, so that's where you want to be. All right, now remember, there's no makeups, no makeup exams. The way that we handle absences is by dropping the exam. That's your dropped exam. If you've missed 2 exams, you're in a world of hurt. All right, now here's the thing about exams that you cannot evade. That is the final exam. And just to reinforce, as it says on the syllabus, it is mandatory and it is cumulative. That means everything since our first meeting in August up until the end of November, or I don't know, what is the... I think our last class is December 1st, if I'm not mistaken. All right, so all that material is going to be on the final in some manner, shape, or form. So be forewarned. And make a note, if you haven't already, it's at 1 p.m., not 1:30. So if you come in at 1:30, just get here at 1 o'clock. Now, so go back in time and come back through the door at 1 p.m. and everything will be golden. And the reason I say that is because exam week, a lot of people for some reason, there's like this internal circuit detector in modern electric alarm clocks, battery powered, and they seem to always detect, not just final exam week, but the morning that you have a final, and they fail. Your exam, and every semester, oh, Dr. B, my alarm clock didn't go off, it worked all semester until that day. So do not let that happen to you. All right, now we're at 1 o'clock in the afternoon, so hopefully you'll be on time. The other class, they have the 7 a.m. final. So there's going to be a lot of, the dog ate my alarm clock type situations in the morning section. But hopefully you guys will be here on time. And the other thing is, if you do come in at 1:30, that's nice, but there might already be somebody finished with a final. Now that's pretty fast for a 100-point final. But it could happen, and if it does, you're SOL. I never let anybody take the exam after the first person leaves. So you got to get in here at 1 o'clock. All right, so kind of engrave. You freshmen, you know who you are. I'm not looking at anybody, but you know who you are, And if you've never been through final exam week, listen, I'm declaring myself your honorary mother-in-law for the next month. Okay, I'm going to be nagging you about it like a mother-in-law. And that is, do not stay up all night studying. You might think to yourself, yeah, this is the great part of college. Yeah, stay up all night studying, and then the next day you come to my final, you're toast. Because your brain won't be working at 100% efficiency. If you want to crush my final, which can be done, you can't do it if your brain's at 50%. To crush any exam, whether midterm or final, you've got to be able to think. And that ain't going to happen if you stayed up till 5 in the morning and then you sleep for an hour or not even. All right? By the same token, do not keep hydrated up. You know, I had a friend, when I was in grad school, I had a friend that was just getting out of undergraduate, and he ended up in the emergency room during finals week. You know, he's studying for some engineering exam or something, and the next thing he knows, he's in the ER. He's got a bunch of IV lines into him, and you know what? He was dehydrated. He was drinking all that Mountain Dew, studying and stuff, and he didn't realize he was dehydrated, so he collapsed or he fainted or something. And his buddies took him down to the ER, and, So don't let that happen. So stay hydrated, eat, work out, and get your rest, because otherwise, now you guys that are juniors and sophomores and seniors, you already know the ropes. All right, but the newbie freshmen, somebody's got to tell you. And I'm going to keep telling you till December. All right. Now, go ahead, question. We'll have our last lecture. I mean, we have lectures up until the end of the semester. I can't remember what the exact last day is because I don't have the syllabus in front of me. But then there's, you know what? What is the exact? Does anybody have the calendar? Because it's a little different this semester. I think exam week starts on Monday. Is that right? Yeah. So we don't have a study day. We go up till the Friday before that, I think, for classes. And you know why that is? Because of football games. Football games. They close campus down for the afternoon, and that screws up the schedule. And this year, it means that we don't have a study day. But you do have the weekend beforehand, so. But anyways, yeah, we'll have regular lectures all the way up past Thanksgiving. We won't have a midterm following those lectures. We'll have a final. So the final exam will be kind of a mini midterm / final. Okay. Question.
What's our schedule on Thanksgiving week?
The schedule on Thanksgiving week? I don't know. We have class on Tuesday. I don't know what you're talking about. Why would I give everybody the day off on Tuesday if Thanksgiving is on Thursday? All right? I know what you're angling for. You're angling for Dr. B says, oh, no class on Tuesday. Incorrect. Nice try, though. All right? You're up here in the front row. Didn't work. It wouldn't work in the back row. It wouldn't work anywhere. We're going to have that lecture. Because you know why? I mean, I might be tempted on another year, but this year we've had the hurricane. We lost 3 full lectures. So it's just, we can't take any holidays. All right, let's take a look at this graphic that we had in homework 9 that you all did. I spent a good hour getting this graphic fished up and colored up the way I wanted, with the U filter and the I filter kind of gray, but different colors of gray. And the different reds and blues and everything. And I looked up the wavelength of indigo and stuff like that. So what I want to talk about is the lower half of this. In other words, the bandpass filters. Okay? Now I want you to make a sketch of this diagram. This is a diagram of the transmittance for UBVRI filters that you put on the front end of a telescope, and this is the set made by the Andover Corporation up in New Hampshire. There's other companies that make them. They get a special glass, or a special form of silicon, and it screens out everything except infrared, or everything except a very narrow band of reds and oranges and yellows. And so that's what we're going to talk about now. On this graph, the vertical scale is the transmittance. And that means how much light is transmitted, and it goes by wavelength. So, for instance, if you look at this big one in the middle here, let me get my cursor. All right, here's the V pass band. Okay, the green one here in the middle where my cursor is, it's marked with a capital V. That's the tallest of the 5 curves. Okay, they're all pretty good. That's the tallest. What that means is that right around 500 nanometers wavelength is where the bulk of the light goes through. And you're getting some 500s, you're getting some low 500s, you're getting some high 400s. But once you get down to about 460 or so, you're not getting much. The green curve dips all the way down. So the low part means you don't see much at that color. If it's up high, that means you're getting a lot. Almost all of it. Now, 100% would mean you do get all of it. Okay, so the higher these are, the more transparent they are to the color that you're looking at. So about 500 nanometers for the V filter. Now, I always thought that was V for visible, and I think maybe in the olden days that's the terminology they used, but it doesn't cover from 400 to 700. And the horizontal scale, that's nanometers, starting at 300. And just for safety, let me put in the 400 nanometer line there on the left in dark blue, and on the right the 700 nanometer line. And hey, just for extra safety, here's the 500 and the 600 nanometer lines. And you can see that the peak, they're all separated. The different filters permit different bands of light to pass. Now that's like you looking at, you know what it's like? It's like if you go to the dollar store and you buy some sunglasses that are green, and you buy another pair of sunglasses that are red. And the dollar store, they're really cheap. But if you buy some red-colored sunglasses, that means everything looks red. All right? And if you look at somebody with a green shirt or a blue shirt, it's going to look gray. But if it looks like a red shirt, it's going to look red. Right? The same thing with green. If you take the green sunglasses from the dollar store, something that's red or blue is going to look gray. All right? Because you're not going to get much from that. All right? It's the same thing here. So these filters, here's what they look like. You put them on the front end, or possibly the eyepiece of your telescope. These little ones are for the eyepiece, and the big ones up here are for the front end of your telescope. And they make, all kinds of different sizes and, clarity and so forth, different hardnesses and stuff. You can look it up on their website. But here, let's take a look at it in close up. And there's my 400 nanometer lines. And we're going to do some iClicker questions here in a second. So go ahead and make your sketches really good. And I'm going to ask you some questions on the iClicker. Go ahead and turn them on. Not yet. And we're going to go through the process of thinking the way that an astronomer would think about the light that he sees, the light that he filters, the filter lets through, and the light that's absent, and what the comparison means with the different filters and so forth. But let me pause here for questions. Yes?
The wavelength from 400 to 700, that's the visible light?
Yeah, 400 to 700, that's the notional boundaries of the visible. All right? And there's no hard and fast boundary that, like sets off an alarm, if you go below 400. So you might go to 399. Some people might be able to see that, 702 nanometers, but roughly 400 to 700. So, question?
The bottom of the image, when you filter the John and you, is that stuff we need to know as well?
Now that's the part number. P/N, that's the part number. This is from a company that makes, this is how they sell them. An astronomer, whether amateur or professional, is going to look at the spec sheet here, look at this diagram. Okay, let me order the part number. And this one, they have B-XX. Now what that means is that if you have to look up the actual filter that you want, because the numbers XX change with the size and so forth. So, but anyways, that's all that is. All right, another question. Good to see you get here. We're almost starting to click. Get your clicker. Not even paying attention. Yeah, get your clicker ready. You guys ready? All right, let's go. And I want you to think visually. All right, this is visual thinking. All right, the first one is kind of easy. Which filter is good for observing a star that has lots of ultraviolet? And definitely consult with your neighbor, talk it over, see if they agree with you, if they disagree with you. You can do it in class, you can't do it on exams, but right now it'll be helpful. Wow, everybody started talking. Pretty nice. All right, 30 seconds. Ding. Hey, my fingertip didn't do it.
Oh yeah, Sarah did it.
I have to touch it a little harder next time. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Zip, zap. Yeah, pretty good, you guys. Most of you got it. The U filter. Yeah, ultraviolet. Yeah, and here's how for those of you, let's see, we got about 40-something students. For the 43 students that missed that one, yeah, what you want to look at is on this graph, the ultraviolet region. So that's below 400. In this case, to the left of the 400 nanometer line. And the filter that has a peak there is the U filter. Everything else is pretty small. All right? Next question. And just so go ahead and jot this down in your notes. This is really what we're trying to think with. We're trying to make distinctions. For instance, on this figure 3 from section 5.2, the key feature for us is the temperature and the peak color. The surface temperature logic, as I made it last time. So for instance, this 6,000 Kelvin star here, did I say star? Yes. That's what when we map out the spectrum of a star, we're thinking, us astronomers and astrophysicists, we're thinking about this a lot. And so here's a 6,000 Kelvin star here, peak in the greenish yellow, just like our star, 5,800 for the sun. And then here's a little cooler surface temperature, 5,000, and it's in the reds. The peak color's in the reds. So, so how you see a star, depending on the filter that you use, it's basically going to reveal a lot. So our surface temperature logic is locked up in these filters or is brought out by these filters. So let me ask you another question. Question 2, multiple choice. Which one's least useful? for observing ultraviolet stars. And you know, the Hubble Space Telescope and other telescopes on Earth, actually not on Earth. Ultraviolet's hard to see from Earth. But space telescopes are pretty good for ultraviolet. You know, we can see a lot of stars that are really bright in ultraviolet, so. But this filter you wouldn't want to really use. All right, 20 seconds. Select select that. No, I was going to say select the window. That's probably why.
Oh.
Yeah. No, it's not why. Okay. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ching. All right. Yeah, most of you got that one right. And again, this one, here's what you want to think about. The eye filter it's pretty good for infrared. And there's lots of stars and lots of humans that emit peak in the infrared. Now this filter is not going to catch many humans. It's still a little hot for humans in this passband. But there's stars, yeah, and other objects in the universe that emit a lot of infrared. So, you know, that's a good one. And the way that you want to think about this, you look at the peak. Are you writing this down? You making a note of this? You look at the peak for each of these pass bands. And then to the left and right, the curve goes down, and pretty quickly, it goes real close to the 0 point on the vertical axis. That means you're getting some, for the eye filter, you're getting plenty of infrared, but then you're hardly getting zip zap over here in red. You know, but look at 700. Bing, you're not getting jack. All right, and by the same token, out here at 1200, that's infrared, but you're not getting much out here either. So it's, you know, for this particular filter, this astronomical filter, the eye filter, you're getting some infrared, but not all the infrared there is to see. All right? Question?
Okay, do you see like in the B line, like where it like skips up a little bit? Like what is
Good eyes, Desiree. I was about to mention that, so thanks for pointing that out. It saves me the trouble of pointing it out for you. And that is, look at the B passband line to the right. Now here's the peak up here in the 400s. Okay, that's blue. You know, that's nice. The blues and the indigos and the violets. All right, let's cut to the right. We steadily go down. Okay, we're still getting some of this green stuff over here. We're going up to the greens, but we're not getting as much. We're still getting some. Oh, we're not. It's petering out. And down here, right about 500, it goes down to zip. But then, look at this. Whoops. It boops upward a little bit. All right, so that means that you've got for this filter, it's got a kind of a glass that has got a little tiny bit of transmittance right there. That's in the reds. It's got a little bit of red leaking in there. You know, so these filters aren't perfect, you know, but there's ways to narrow things down and isolate colors really carefully. But this is this passband filter theory. Now, next question, a little bit tougher. Let's see if you got your brain on. All right. So if you have your brain on, you're going to be able to hack this question. Our star, the sun. What do you know about the S-U-N? What do you know about the energy distribution by wavelength for the S-U-N? 30 seconds. No, let me try it. Let me try it.
All right.
Just click the window.
Okay.
Okay. Dude, this worked before.
I saw
Oh,
you.
maximize it. Maximize it.
Okay.
Dude, what's wrong with my fingertips?
You just,
Huh? Dude, okay, you better click it.
okay.
It's burning my grits here. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Bing. Yeah, what's the brightest color for the sun? Yellow? No. No. Ah! I've said it about 1,000,000 times. Green, yellowy green. And, okay, show them this one. Show them this one. Now look, here's how you voted. So I believe that I caught a bunch of you napping. You've got to think about, what the graph tells you. The sun is not yellow. It's greenish yellow. It's green. To us, it looks yellow because, we're at the bottom of this deep atmosphere. But yeah, if you were on another star and looking at the sun, they'd say, oh yeah, there's a green star over there. We'll call it Bob or whatever they want to call it. So yeah, so if you got nabbed by this one, now let's take a look at what it's not. A lot of you voted for R. I see your question. Hold on. A lot of you voted for R. R is nice, and the SUN's got a lot of R, but you know what it's got more of? It's going to be brighter in this because V is right at the center of the brightest part of the sun's spectrum. Now, R's over here, but look at R. R's getting a lot of it's got a lot of infrared. That's nice. But the sun's kind of boring in infrared. I mean, it puts out a lot of infrared, but this is where the action is, over here in the V. So the V filter, I remember asking my astronomy professor, is it V for visible? And supposedly the answer is yes, in the olden days, but it's not really, it doesn't cover all the Roy G. Biv colors. But, somebody decided they're going to call this photometric filter V for whatever reason. Now the I, you can see that one. The U, you can see that one. That's good, but V is, instead of calling it the G filter, they call it the V filter. Now, I'm going to burn your brain. So don't drop your clicker out in the aisle or any other place, and I want you to think, and I want you to think real carefully. Now I'm going to ask you not about the sun, but about a hot blue star. Here it is, question number 4 for today. Read carefully and make a decision. And you're going to need to look at your diagram of the filter curves. How do you take notes on a computer? How do you make that sketch on a computer? Can you do that?
No, you look the graph up on Google, and then you put it on.
What? You're using Google in lecture?
I mean, only for the picture.
Dude, sweet. Is it the same one that I have, though? Is it from that? Yeah, you could get that same exact one if you dial in the name of the company and stuff. No, but the reason I asked you that, Tali, is because some people, they draw on their computer. They have I've seen that. And usually this thing works as a touch screen up here, but it's not working as a touch screen today.
I know.
So talk with your neighbor. If your neighbor's smart, or if you're smarter than your neighbor, you might have a conversation. If you're sitting there and nobody's sitting next to you, just use your coconut. You know, this round blob of supposed brain tissue up there at the end of your neck, the top of your spinal column. "30 seconds. Okay, Connor Nichols of the Clan MacLeod. The Highlander. Did you ever see that movie? The Highlander? Connor MacLeod of the Clan MacLeod. There could be only one.
You're too young.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And yeah, you guys did pretty good. Yeah, so here's how you... All right, now, a few of you, 66% of you voted correctly. Now, a bunch of you voted for A, and here's what you got to think. If you have a hot blue star, it's not going to be brightest in the green, in the V filter. It's going to be hotter in the blue, or it's going to be brighter in the blue. So you're going to see more light coming through the B filter than comes through the V filter. But you know, the thing is, there's going to be a temperature where B and V are the same. You know, where you get the same amount of V as you get for B, and you know, that's a certain kind of a star. You know, a certain temperature, yeah. I mean, there's a temperature where they're the same, but B. Now, C. If you voted for C, there's 10 of you that voted for C. No way, Jose. Because, no, I'm not making fun of you, but I want you to think about what that answer says. A hot blue star is not going to appear red in a B filter. The B filter is going to let through blue. So you're not going to see any red. All right? The same thing, the V filter is not going to let any blue, well, not much blue. It's going to let mostly green through. And that's the pass band for the V filter. All right? So you might see something like this for the midterm. Just saying. All right? And so the bottom line for this line of questioning, see, I've been cross-examining you. You're all in the witness stand. I'm trying to get you to budge. I'm trying to interrogate your mind. So the bottom line is to remember is measuring the brightness in different filters can tell you a lot. You know, is it bright in the R but not in the V? All right, that tells you something. Is it bright in the U and pretty pathetic in the V? Well, that tells you something. What about U, B, and V? What if you measure in all three of those? How do they stack up, you know? So you have all kinds of options, and by looking at it carefully, you could tell a lot about a star. And the way that we do that, numerically speaking, by rating the brightness, is by something called the color index. All right? Go ahead and write that word down. The color index. The color index is related to, or is a computation based on what you see in two filters. B minus V, or U and V, or R and B. There's all kinds of color indices, and they're all related to something called the magnitude system. Now, I told you in the homework that we're not going to do a huge amount with magnitude system, but I do want to give you a little bit of a rundown so that you can understand the color index. All right? To understand that, we have to talk about apparent and intrinsic brightness and luminosity. So let's take a look at that. All right, now, as we talked about or as you read about in the readings in chapter 17, if you want to measure the luminosity of a distant star, you have to first compensate for the dimming effect of distance. All right? And to do that, you've got to know how far away they are. In other words, you have to know the parallax distance, hopefully, or some other way. I mean, there's ways to even measure the distance to galaxies. Not with parallax, but with other methods that we'll talk about next week after the exam. And the general effect is this, that the light intensity, and this is a great diagram. This is diagram figure 4 from chapter 5.1. So don't forget that on exam 4. We're going to be dipping back into chapter 5 and stuff, as well as the stuff that we're in now in chapter 17. The light intensity drops off by a factor of 1 over the distance squared. And this diagram is how we're going to work that out numerically. And you're going to do a numerical question in a minute that involves calculating relative intensities, or actually a flux level. So what you do is you measure the apparent brightness here on planet Earth or from orbit. So you go to the top of the Mauna Loa or one of the volcanoes in Hawaii, or one of those mountains in Arizona or New Mexico, or down in South America in Chile, and you measure the brightness of the star. And then using the distance, you calculate backwards, and you get the intrinsic luminosity of the source. Now, let me give you an example of how why you've got to do that. If you go up to, like, for me, the darkest place I ever went was one time I was up in the mountains of Montana with some friends, and we were driving to a campsite up in the mountains, and it was a night that there was cloud cover. And that's not very common in Montana, but that night there was cloud cover, so there was no moon, no stars, no nothing. And it was after sundown, so it was really dark. There were no city lights. Once we turned off the car, and shut it down, no headlights from the car, no nothing. And oh my goodness, it was so dark you couldn't even see your buddy standing 2 feet away from you. All right? Now, the same thing could happen here in Orlando. No, it couldn't happen here in Orlando. And, you go up to Ocala National Forest. You know where it would happen, though? If you go to sea, if you go out far away from land. And I've heard that sailors in the Navy, when they're out at sea, can see some beautiful starry nights when it's clear. But if you go up to Ocala National Forest, it'll be pretty dark. You turn off all the lights, you get away from the campground, people with campfires and stuff, or down by the beach or something like that, and you look up and it's totally dark. So so you got to be in a totally dark place, because you can't see the object that we're going to talk about. And so I'm going to talk about 2 different objects. A flashlight, and a flashlight has a little, like a little bulb about as big as your thumb, big as your thumbnail. All right? And then compare that to a 60-watt incandescent bulb that you buy at the hardware store. All right? Now, if I see one light source, a few steps away from me so that I can't actually see the filament and I can't really, it looks like a point source, so the other end of the aisle here, but I don't know what its brightness is, I can't really tell how far away it is. So one way to say it is, if we totally darkened this room, like the mountains of Montana or Ocala National Forest, no lights in here, and somebody had a flashlight bulb and a 60-watt bulb at the end of the aisle here, No, that's not a good example. Maybe a little further away. Maybe over by the Ed building. All right? If it was totally dark, and you'd see, either of them. But the 60-watt bulb would be a little bit brighter than the flashlight bulb. You'd see both of them, probably. And so what that means is that if they're at the same distance, the apparent brightness tells you the actual wattage rating of the bulb. Let me repeat that. If both of the objects are the same distance away, comparing the brightness tells you the absolute wattage rating of the light bulb. All right? So jot that down. If both light bulbs are the same distance away, then your visual comparison of the brightness tells you which one's got a higher wattage rating and which one's got the smaller one. All right? But now think of a same night, totally dark, no Disney lights, no Universal lights, no city lights to glare up things, just totally dark. You can't see your hand in front of your face. Now, keep the 60-watt bulb over at the Ed building and move the flashlight bulb up to the parking lot here or closer. And if you do it, at some point, they're going to seem the same apparent brightness, but they're going to be different distances. All right? So the second lesson of distance and apparent brightness is this. Two objects can appear to have the same apparent brightness, but be completely different distances away. If one of them's brighter but way far away, it's not going to look as bright as the dim bulb that's a little bit closer. All right? So this whole idea of distance and stuff, we got to get a handle on it. Because if everything, the stars are all different distances. So just looking at a star and saying, oh yeah, that's bright, like Sirius. But that doesn't mean that Sirius is the absolute brightest star in the universe. It's not. Because we're actually relatively close to Sirius. It's bright, it's brighter than the sun, but it's not the brightest of all. And we're going to look at some that are intrinsically brighter. So that's the difference between intrinsic luminosity and apparent luminosity. Intrinsic brightness and apparent brightness. Intrinsic magnitude or absolute magnitude and apparent magnitude. All right? So magnitude, luminosity, brightness can all be either intrinsic or apparent. Intrinsic is what's written on the light bulb, on the box that the light bulb came in, 60 watts. Or, for a light bulb, it might be half a watt, or a quarter of a watt, depending on the light bulb. Right? That's the intrinsic brightness. That's the intrinsic amount of energy per second that's blazed out by the light. But apparent brightness is what your impression of it, depending on where it is. Okay? And if you bring them just to the right distance, the 60-watt bulb way far away and the flashlight bulb in close, to your eye, they look the same brightness. Okay? So we've got to get a handle on that. Now, let's look at this diagram up close. This is from the chapter 5. And let's say that here, the same star at one distance unit away, so this could be like one astronomical unit for this star. Let's say that the flux is 360 watts per square meter there. Okay, so go ahead and make a sketch of that. And here's your central source. Here's your star. And then 1 unit out, the lights, it only spreads out to this 1 square meter. But now, if you double the distance out to here, you're now 2 units away. That same amount of light is spread out into 4 squares of the same size. So here, you have this 90 watts per square meter out here. And we've talked about that before. You know, Earth, it's 1367 watts per square meter from the sun. And out at Mars, it's, hundreds less because it's further away, right? So the numeric pattern, I forgot your question. What's that?
They answered my question.
Who did? Oh, the brain trust back there? What's that?
It was from your notes.
Okay. Okay. All right. Where was I? Yeah, the numeric pattern is this. If you double the distance, the dim down factor or the diminution factor is 1 over 2 squared. All right? So 1 over the square of the distance. So when we say that it's inversely proportional to the square of the distance, yeah, that's what it means. It's just because the light spreads out. And the surface area of a sphere is 4 pi r squared. So it's covering, all the light from the sun covers bigger and bigger spheres as it goes out. So the distribution per square meter on bigger and bigger spheres is less and less and less. And the shrink down factor, for instance, this one, when you go out 2 units, it's 1 over 2 squared, 1 over 4. So that makes it 90 watts per square meter. Now, you might think to yourself, Dr. B, what is it out here at 3 times the distance? And I'm going to ask you that next. All right? So here we go. Hit the refresh key on your calculator. Go ahead and start the question. And go ahead and calculate using this theory here, inverse distance squared, to figure out the flux F at 3 times distance. And you're going to type in a whole number of watts per square meter based on 360 at 1 unit out. So now we're 3 units. We know what to do at 2 units out. So now what do you do at 3 units out? Okay, 2 units out, it's 1/4 of that. So what is it now at 3 units out? You can see people are flailing. See, that's 90 divided by. I don't know what that is. That's a miscue of some kind. That's not right. I'm going to see different. Somebody had this. What is that? Oh, I know what that is. That's this times 360. For those of you, everybody, I'll give you a little pro tip here. It's going to be something less than 360. Because you're further away, it's going to be dimmer. Okay? So you're going to see this thing empty out, hopefully. So talk to your neighbor, consult. And I can see you guys doing that. Definitely. So Asia, Madison, Talia, yeah, you guys. What do you got? Talia. Yeah, type in the number and hit the send key. Good.
Yeah, I think so. Because okay, the fraction I got is 1/9, and then of course we need to use you would multiply because you
Yeah, that's
can't
right. I just
divide.
did 1/9.
Yeah, concept, yeah. Yeah, and I got 39.
Ching! Cha-ching! 2 to the tooth, yeah. No, it's right there. That must be what some of these are. What's Remember, it's inverse r squared. Inverse r squared. 30 seconds. You guys are doing good, but there's a few errors here. Ten seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Go ahead and let's look at this. All right, I'm going to show you the rundown here. And the correct answer is 40. Here's how you do it. I mean, the distance is 3 times, so you go 1 over 3 to the second power. That's 1 over 9. 1/9 of 360 is 40, so 40 watts per square meter. All right. Now, some of these answers, 120, you know what that is? 360 divided by a third, or divided by 3. You forgot to square it. It's always the distance ratio to the second power, and then divide by that. So whatever your flux is at 1 unit out, at 3 units out, it's 1/9 of that. Can you go down the list? Let's take a look at some more errors here. I don't know how you get 203. 45 is 360 divided by 8. Is that right? Yeah. Oh, you know what that is? 360 divided by 8? That's 2 to the third power.
No, they just took half of that.
No,
Or
it's
the 40, like the 45.
yeah, so it's 2 to the third power. 1 over 2. It's always 1 over the distance ratio to the second power. Go ahead and switch back to the... Go ahead and make a note to yourself. It doesn't matter what the distance ratio is. 1 over 2 squared for twice the distance. 1 over 3 squared for triple the distance. 1 over 4 squared for 4 times the distance. And, it could be 2.5 times out. So 1 over 2.5 quantity squared. So that'd be, it's not a nice whole number. 1 over 2.5 squared is 1 over 6.25. But you could figure out, how many watts per square meter, maybe round off or something. So it's always 1 over the square of the distance ratio. Now, why do we care about that? Well, in the solar system, watts per square meter drops off in that manner. Now, the astronomical unit for Earth is, it's 1, and the distance out to Pluto, or the distance out to Mars is bigger than 1. So, it's got a distance ratio, 1 over 1 point something squared, and then you multiply that by 1367, and you get 589 watts per square meter out there at Mars's orbit. Out there at Neptune's orbit, you're way out there, and so you have 1.51 watts per square meter. So, but the thing is, watts per square meter is okay in the solar system for rating the brightness of the SUN, or the apparent brightness of the SUN. But for stars and stuff, it's a little shaky. So what we do with stars outside the solar system, is we use something called the magnitude system. And we use other systems as well. But one of the alternate routes was invented by the ancient Greeks. And they said, all right, I'm going to rate the brightness of stars as first class brightness. That's the brightest stars. Second class of brightness, that's the second brightest group of stars. And on down, and they said, all right, and we're going to make the sixth magnitude of stars the very dimmest that the sharpest eagle eye person can see. All right? Now, in the modern system of magnitudes, we do the same thing. A small magnitude number is bright, and a big magnitude, a big positive number, is dim. And what we do, instead of using the visual, list that the ancient Greeks used, we now use vega as the 0 point of the magnitude system. So if something looks brighter than vega, it's going to have a negative number. If something looks dimmer than vega, it's going to have a positive magnitude number. All right? And so vega is it's kind of like our benchmark star in the magnitude system. So what that means is, for instance, Sirius is about a apparent magnitude of -1. So the symbol for the magnitude is little m. Thank you for doing that. All right, so little m equals -1 for Sirius. Mental IQ test question. Sirius, that's the brightest star in the sky, right? No. What star is brighter than Sirius? Polaris, Vega? No. The sun. And ding, I got you. The sun is the star. And its apparent brightness rating is -27. Oh my goodness. So rating the sun with the apparent magnitude system is not very practical. But other stars, yes. Okay? So Sirius is just an example. Let's do a table. All right, so here's our table. All right? And go ahead and make a note. And up at the top, we're going to have the sun, and we're going to have its apparent magnitude. Then we're going to do the full moon, Venus, Sirius, and then Vega in the middle. That's my anchor. Then Alpha Centauri A, Antares, a red giant, Polaris, and then the the nucleus of the Andromeda Galaxy, which you guys, a lot of you observed at the observatory, that kind of smudge of light that you could see with that galaxy. Now the top of this table, I should say, is the brightest objects, and for us it's the SUN. Dimmer as you go down. So Vega's kind of in the middle there, right? And let's just lock in 0. So that's our anchor point. Now the thing about apparent magnitudes and absolute magnitudes that I'm not going to show you how to do is how the parallax distance allows you to compute the magnitude of the star. Because it involves a lot of logarithms. But we know that the sun is apparent magnitude -27. Here's the full moon, -13. And here's Venus, -5. And everybody knows Venus, the morning star, or Venus, the evening star, part of the year, is pretty bright. And a lot of times people think it's a UFO, but it's really just Venus. And here's Sirius, -1. Now, that means that Sirius is the brightest of the stars in apparent brightness, little m. But now, if you were a different distance than we are from Sirius, it might be really pokey if you're way far away from it. If you're even closer, you might even if you not get close enough to it, it might look like a -5 or even a -20. I'm sure there's a distance from Sirius where you could get to -27. Alpha Centauri A, 0.01. So just a little smidgen dimmer than Vega. All right? It's a positive number, not 0. Antares, a red star, a red giant. It's still pretty good. It's magnitude 1, but that's dimmer than Sirius. It's dimmer than Vega. It's dimmer than Alpha Centauri. All right? Oh, and by the way, Alpha Centauri A and our sun are very similar stars. And the sun is minus 27. Alpha Centauri A is a 0.01. So that tells you something right there, that distance makes a difference in the apparent magnitude scale. Right now, Polaris 1.97, even dimmer. And then the nucleus of the Andromeda Galaxy, 3.44 approximately. You can see it with your naked eye on a good clear night. And I've seen it. I decided to find it one night up in Maine, sitting on a dock out in a lake, good clear night. You know, I had my star atlas, so I could kind of figure it out, a little flashlight. Now, the problem with this table is, look at this. This is like saying, okay, the full moon and Venus are brighter than Sirius. What? That's no good. All right, so that's a problem. And that's why we call this the apparent magnitude. Now, the magnitude that you measure, if you were 10 parsecs away from each of these objects, this is how we get the intrinsic magnitude, or the absolute magnitude of a star. It's intrinsic brightness. All right? And that's the second column here. So that's what we're going to tackle now, this one over here. So this is like what I said. If you put the flashlight bulb and the 60-watt bulb over at the Ed building, then and you look at them, you can, okay, yeah, the one on the left is flashlight, the one on the right is the 60-watt bulb. You can tell them apart, same distance. All right, now we're saying, all right, what would be the brightness of these stars, the intrinsic brightness, if I was 10 parsecs away from everything? Now, 10 parsecs away from the SUN, 4.83. That's pretty dim. The sun, it looks bright to us. The sun of justice. And it rules our planet. It rules our weather, climate, everything. But it's no great shakes. And forget about the full moon. Forget about Venus. They're zip zap. If you were 10 parsecs away from them, you couldn't see them. Yeah, because they just reflect a little bit of sun light to us, but that's about it. Now, Sirius, 1.42. Now, I'm going to give you a mental IQ test question here. All right, so I want you to use your powers of logic. Is Sirius closer than 10 parsecs or further than 10 parsecs from us? The absolute magnitude tells you its brightness at 10 parsecs. The apparent tells you its brightness at its true distance. So is it closer? Raise your hand if you have an idea. Is it close? What do you think, Chenille? You think it's further? So if it were further, in truth, then its magnitude number would be bigger than 1.42. But is it bigger than 1.4? No, it's not. So Chenille, it's got to be closer than 10 parsecs. Go ahead and write that down. Looking at the apparent and the absolute magnitude, it encodes the distance. Now you can't. Now to tell the exact distance in parsecs, I'd have to give you some logarithms and stuff, which I'm not going to do. Now here's Vega. The same question. Is Vega farther or closer than 10 parsecs? True distance, 10 parsecs. Okay. The true distance is the apparent, is the second column. It's encoded in that. So it's a little bit dimmer than what we see. All right? So what we see is brighter than 10 parsecs. Therefore, it's a little bit closer than 10 parsecs. So that kind of tells you, Vega is fairly close to us. Alpha Centauri A. Right, 10 parsecs away. And apparent magnitude quite a bit smaller, so it's definitely, we know it's about 3 light years, about 1 parsec away. So, Kayla?
Sorry, is magnitude a measure of brightness, or what does the unit represent?
The unit, it's not a unit, it's just a number. So there's no watts or square meters or anything. The magnitude is just a pure number, and it's a rating of brightness following the Greek pattern. The smaller the number, the brighter. And in fact, the deeper into the negatives, if you do have a negative magnitude number, the brighter. The higher the number in the positives, the dimmer it is. All right? And this table is going to kind of, now look at Antares. Oh my goodness. This one, the apparent magnitude's 1, which is nice. But if we were 10 parsecs away, oh my goodness. That'd be, check that out, it'd be brighter than Venus. Oh my goodness. So that tells us, we're not even close to 10 parsecs away from that baby. Now to figure out the distance, to get the absolute magnitude, you have to know the distance. You got to do logarithms and stuff like that. But we do that, and we encode that for Polaris. Polaris is pretty good. It's negative. You step back 10 parsecs away from it, or actually, you get in a little closer to 10 parsecs than what it truly is, and you have an absolute magnitude of 3.63 negative. And the Andromeda Galaxy, you can't really do that because Andromeda Galaxy is way bigger than 10 parsecs. So, anyways, the bottom line for us is the apparent magnitude ratings and the UBVRI ratings, the brightness ratings in B and V, R and I, whatever pair you do, tell us a lot about a star. And here's what it tells us. This, my wonderful students, is called a color luminosity chart. Go ahead and write down that vocabulary term, color luminosity chart. On the vertical axis is luminosity, and this one is multiples of the luminosity of the sun. So that's another. And Kayla, this one, the units are luminosities of the sun. So we measure brighter at the top, and you see that number up there, 10 to the 6th, that's 1,000,000. There are stars that are close to 1,000,000 times brighter, absolute brighter luminosity than the sun. And there's stars down here that are pretty pokey, 1,000th of the luminosity of the sun. Right? So this is another way to orient your brightness scale, your vertical scale. On the horizontal scale, surface temperature, color, and what is this? B minus V? That, my wonderful students, is a color index. The color luminosity chart, also known as the HR diagram, the Hartsprung-Russell diagram, which you can read about in chapter 18.4. This is from figure 3. The horizontal scale can be rated in surface temperature. Sometimes you see it that way. Sometimes you see the peak wavelength, lambda max. Sometimes you see the spectral type, and you guys read about that. That's the old-fashioned way. But we still use spectral type. OBA, F, GKM. And that's just, that goes all the way back to the 1800s, those letters. Color. surface temperature, and using the UBVRI color photometric system, B minus V, color index. You can write that on the horizontal axis as well, which is the previous slide, this one. You know, B minus V. So these are magnitudes, all right? So on the color index, take a look at this. Don't try to write it down, but just try to look at it and listen to what I'm saying. These are magnitudes. So you measure the magnitude in the B filter. You measure the magnitude in the V filter, and you subtract V from B. B minus V, that's the color index. All right? Now, if it has a negative value, that means it's blue. It's brighter in the blue. If it has a positive value, that means it's redder. So this is a 1.8 color index over here, B minus V. And so those are the red stars over there. All right, so a lot of times you'll see these HR diagrams with a color index. Sometimes you'll see it with a spectral class. And this one over here, this one's the luminosity, the SUN as well. Sometimes you see absolute magnitude, capital M, on this scale. Now here are the two guys that figured this out, Hertzsprung and Russell. About 100 years ago, they saw this pattern. Look at this. All the stars in the galaxy follow this. You know, most of the stars in the galaxy are on this diagonal. It's called the main sequence. And why is that? Because they all have the same physics at the core of them. They're all burning hydrogen. They're all fusion reacting stars. Same thing over here, but now these are mature stars. They've turned into giants. These ones are dead stars, white dwarfs. You know, they've run out of nuclear fusion material. But most of the stars, yep, right on this pattern here. And we'll be talking about this on Tuesday. So your homework assignment, study the Hertzsprung-Russell diagram, the HR diagram, the color luminosity chart in 18.4. We'll see you on Thursday. You're dismissed.